Hey folks, how's it going? In this video we're going to go over exactly what you need to know and be able to do for the Quanta topic in the Advanced Higher Physics course. So let's get started. Now the SQA split the Quanta topic into three key areas. So we have Introduction to Quantum Theory, we then have Particles from Space, and lastly Simple Harmonic Motion. So we'll go through each of these key areas in turn and look at what you need to know for the exam. So first of all, if we look at Introduction to Quantum Theory, it says you need to be able to know of experimental observations that cannot be explained by classical physics but can be explained using quantum theory. So things like blackbody radiation curves and the ultraviolet catastrophe, the formation of emission and absorption spectra, and the photoelectric effect. So these are all things that can be explained using quantum physics but not classical physics, and it helps to be able to go into detail to explain all of them. It then says you need to use an appropriate relationship to solve problems involving photon energy and frequency. So remember E equals hf, which was an equation seen in higher physics, where E is the energy of an instant photon, h is Planck's constant, and f is the frequency of the photon. Next, you need to know the Bohr model of the atom in terms of the quantization of angular momentum, the principal quantum number n, and electron energy states, and how this explains the characteristics of atomic spectra. So remember, it's electron transitions, i.e. electrons moving up an energy level or down an energy level in the Bohr model of the atom, which leads to the lines on a line emission spectrum. And remember, we saw that the angular momentum of electrons in atoms is quantized, which just means it's equal to a multiple of a fixed value. It then says you need to use an appropriate relationship to solve problems involving the angular momentum of an electron and its principal quantum number n. So we have mvr equals nh over 2 pi, where mvr can also be written as your angular momentum capital L, and this is equal to an integer number n times Planck's constant over 2 pi. So notice how h over 2 pi is a constant itself, so that's just going to give you a fixed value, but the whole number n, which is your principal quantum number, will change the value of this depending on what it is, i.e. as to which energy level you're in. Moving on, it says describe experimental evidence for the particle-like behaviour of waves and for the wave-like behaviour of particles. So remember, we have things like the photoelectric effect and Compton scattering for the particle-like behaviour of waves, and then we have things like electron diffraction for the wave-like behaviour of particles. Next, it says you need to be able to use an appropriate relationship to solve problems involving the de Broglie wavelength of a particle and its momentum. So remember, we have this equation lambda equals h over p, where lambda is the wavelength of the electron, h is Planck's constant, and p is the momentum of the electron, which remember you often have to expand into mass times velocity, p equals mv. So it's helpful to remember that you can write lambda equals h over p equals h over mv. Next, you need to know that it is not possible to know the position and the momentum of a quantum particle simultaneously, so that's getting into the Heisenberg uncertainty principle. Likewise, with energy and time though, you should know that it is not possible to know the lifetime of a quantum particle and the associated energy change simultaneously. And then you need to be able to use appropriate relationships to solve problems involving the uncertainties in position, momentum, energy and time. The lifetime of a quantum particle can be taken as the uncertainty in time. So you need to be able to use delta x delta px is greater than or equal to h over 4 pi, and delta E delta t is greater than or equal to h over 4 pi. Lastly, for section 1, you should know of implications of the Heisenberg uncertainty principle, including the concept of quantum tunneling, in which a quantum particle can exist in a position that, according to classical physics, it has insufficient energy to occupy. So it's important to be able to explain quantum tunneling and to be able to give some examples of where it occurs, such as in alpha decay or in a scanning tunneling microscope. Moving on to section 2, particles from space, you can see this one's a wee bit shorter, but there is a lot of overlap in this section with charged particles moving in a magnetic field from the electromagnetism topic. So firstly, you should know the origin and composition of cosmic rays and the interaction of cosmic rays with Earth's atmosphere. So you need to know what the cosmic rays are mainly made up of, so remember that's protons and alpha particles, and you should know that when they strike the Earth's atmosphere, they produce secondary particles in a cosmic air shower. You should also know the composition of the solar wind as charged particles in the form of plasma. Moving on, you need to be able to explain the helical motion of charged particles in the Earth's magnetic field. So remember, that's due to the charged particles entering the Earth's magnetic field at an angle, and therefore we have two components of the velocity vector giving rise to the helical motion. So these are the velocity component perpendicular to the magnetic field direction giving rise to the circular motion, and also the velocity vector parallel to the magnetic field direction, which gives rise to the pitch in the helix. Lastly, you need to be able to use appropriate relationships to solve problems involving the force on a charged particle, its charge, its mass, its velocity, the radius of its path, and the magnetic induction of a magnetic field. So these are the equations F equals qvb, which is the magnetic force, and F equals mv squared over r, which is your centripetal force. And remember, you've seen both of these equations in the electromagnetism topic, as well as this one, F equals mv squared over r, in the rotational motion and astrophysics topics. Lastly, we have section 3, which is simple harmonic motion, or SHM, and you need to be able to define SHM in terms of the restoring force and acceleration proportional to and in the opposite direction to the displacement from the rest position. So if you're asked to state or define what SHM means, you need to make sure you say the force or the acceleration is proportional to the displacement but in the opposite direction. And that's why we get the negative sign appearing in Hooke's law, F equals minus ky or F equals minus kx, and also in the equation for SHM, which is here, A equals minus omega squared y. You should also be able to use calculus methods to show that expressions in the form of y equals a sine omega t and y equals a cos omega t for the displacements are consistent with the definition of SHM, i.e. that they are solutions to the equation a equals minus omega squared y. So that just means you need to be able to differentiate this expression or this expression for the displacement once to get the velocity, and then differentiate again to get acceleration, and to show that it forms this equation here, a equals minus omega squared y. So I would practice to make sure you can do that. Next, you need to be able to derive the relationships for velocity and kinetic energy in SHM. So we have v equals plus or minus omega times the square root of a squared minus y squared, and ek equals a half m omega squared times a squared minus y squared. So check out my theory videos for deriving these equations if you're not sure how to do that. Moving on, you need to be able to use appropriate relationships to solve problems involving the displacement, velocity, acceleration, force, mass, spring constant k, angular frequency, period, and energy of an object executing SHM. So all of these equations for simple harmonic motion you need to be able to use. So the first one we have is a definition of SHM, but also Hooke's law, F equals minus ky. We then have equations for the angular frequency omega in terms of the linear frequency f and period t, so omega equals 2 pi f equals 2 pi over t. We then have the acceleration equals d squared y by dt squared, which is equal to minus omega squared y. So that is your definition of SHM in terms of acceleration and displacement. We then have expressions for the displacement, y equals a sine omega t or y equals a cos omega t. And remember, it depends on the initial conditions as to which one of these you use. So if the object starts at y equals 0 at time t equals 0, you use the one with sine. And if the object starts at y equals a, i.e. the maximum amplitude away from the rest position at time t equals 0, then you use cos. You also need to be able to use the equation for velocity, v equals plus or minus omega times the square root of a squared minus y squared, as well as do calculations involving maximum velocity. So remember, maximum velocity of the object will be at y equals 0 at the equilibrium position. So if you put y equals 0 into here, then we have the square root of a squared, which just gives you a. So we actually end up with v equals a omega, or omega times a, for the maximum velocity. And likewise, you need to be able to find the maximum acceleration of an object undergoing SHM. So remember, maximum acceleration would be found from a equals minus omega squared times a, where y equals a at the maximum amplitude from the equilibrium position. Because remember, that is where the value of acceleration will be biggest, where the object is either slowing down or speeding up away from the maximum amplitude. So we can say that maximum acceleration is equal to omega squared times a, the amplitude. We then have the kinetic energy equation, ek equals a half m omega squared times a squared minus y squared, which we said before you need to be able to derive, as well as this velocity one. And you also need to be able to calculate the maximum kinetic energy in the system. So the maximum kinetic energy, just like velocity, would occur when y equals 0. So if we put in y equals 0, i.e. the object being at the equilibrium position, into this equation, then this simplifies to ek max, the maximum kinetic energy, equals a half m omega squared times a squared. Lastly, you need to be able to use the potential energy equation, ep equals a half m omega squared y squared. And to finish off, you should know the effects of damping in SHM to include underdamping, critical damping and overdamping. So in the theory video on damping, if you haven't checked that out yet, we looked at an undamped system, an underdamped system, a critically damped system and an overdamped system. And it helps to be able to sketch or visualize what happens to the amplitude over time in each of these 4 cases. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a thumbs up, subscribe to the channel, and I'll see you in the next one. Take care.